computing lab at NYU. Dennis and I are leading it, and currently we have 12 PhD students. During this talk, I'm going to present a lot of different papers, and the students are the one that, of course, did most of the work for them. So today, I would like to give you a very broad overview of what we have been working on in the last 3 to 4 years, and with a special emphasis on everything that we have been doing in the direction of processing large collections of geometric data. So I will start by introducing the ABC dataset, which is our first attempt at collecting a large dataset of geometric shapes that is of a size suitable for benchmarking data-driven algorithms at scale. Then I will move to 2 simulation projects. The first one is going to simulate light, and in particular simulate how a 3D scanner works, and I'll show you that it's possible to have simulations that are so accurate that you can essentially exchange between images generated by a simulator and images taken by a scanner, and it's very hard to tell what the difference is. In particular, what I'm showing here in this chess piece, one of them is a virtual image and one of them is a real photograph, and it's going to be a challenge for the audience to figure out which is which. And then finally, we're going to move to a simulation of physical deformations, which is something that is particularly relevant in machine learning, especially for robotics application. And I'm going to describe a series of projects that we work on in this direction to try to get to a point where we can do a simulation of complex physical interactions in a reliable way and in a way that can be used to generate data for data-driven methods, either for simulation or for robotics control. So let's start with ABC dataset. So this has been originally presented at CVPR in 2019, and then it has been further developed in the more recent years. And what this is a collection of models. All these models are coming from Onshape, which is a company that is selling online software for generating CAD models. And they allowed us to collect all the public documents on their website and to release them as a public dataset. So what is nice about this is that there are a lot of models. There are currently 1 million, and very soon we're going to add another 1 million to this collection. And all the models are in some sense consistent and self-similar because are all man-made objects created using a CAD software. In particular, all these objects are represented as a boundary representation, meaning that it's a collection of patches for which we have an explicit analytical description. And this is very useful because this means that we can extract from this representation many authors that are commonly used in machine learning. For example, it's possible to get a triangle mesh out of it, or extract a point cloud, or assign distance field. And in all these cases, what we can do is actually sample and extract this information at arbitrary resolution. So depending on this method that you're trying to train, you can decide what is the resolution, how many points, or what kind of representation you want to use, and you can extract this information directly from the dataset. One of the thing that we did is to try to make this easy. So the dataset comes with a software that allows to generate data for in formats that are convenient for learning. And this is one of the areas where we are spending a lot of effort. And when we realized that actually converting geometric data between different formats, it's still a very difficult problem. And while it's easy to do if you are willing to engage a user and help with this manual interaction, it's something that is very hard to do if you want to do it in an automated way. So what kind of applications are supported by the ABC dataset? So we don't, unfortunately, have yet semantic informations like categories or where these objects are used, but we have a lot of low-level information, such as how the objects are decomposed into patches, what are the features on these objects, We have ground truth information for differential quantities, such as normals or curvature. And so these are the sort of tasks that are supported right now. I'm going to say a little bit more on what we're doing on semantics in a few slides. But first of all, I would like also to focus on the fact that all this work is not only useful for data-driven applications, but it's also useful for geometry processing, because what we found is that any algorithm that we try to use on such a large collection of models didn't work. Just to give you an example, even computing normals, just by computing normals on faces and then averaging them on vertices, it's something that you cannot do on this large collection, or at least like if you implement it in a naive way, you're going to get for some models some nonce, just because you have like unhappy floating point cancellations. And at this scale, this small possibility of failures actually will lead to trouble. So some examples of what you can do and some of the interesting discoveries that we did while working on this data set is that certain tasks are actually hard to do. And even simple things like normal estimation, which is something that many data-driven methods have been tested on, are very difficult to apply at such a large scale. And especially when there is a huge variety of models going from like tiny ones to very complex models that can be made of multiple components. And one of the sort of discoveries that we made here is that whenever you compare a lot of algorithms together, it turned out that the methods that tends to perform better on average over the entire data set are actually the ones that are not trying to use a data-driven prior, even if they are reasonably close. But the largest surprise of all is that the method that performs best on average is the simplest one, which is just, let's compute normals on faces and average them on vertices. So I think it's sort of like exciting to think of algorithms in geometry processing in a more experimental way. So instead of trying to get a certain result on a small collection, just always test them on massive collection of data and then see like statistically how things look like. And what we found is that every time we did this, we always found sort of surprising results. And I encourage everyone to just give it a shot and see for your own problems, how can this look like? Another thing that we are working on, and we have some preliminary result on the paper in the bottom left, if you're interested, is on how to solve more high-level tasks. For example, how do you extract feature lines from a point cloud? And one of the things that we realize is very challenging is, in general, making these methods scale. Like whenever you have a complex CAD models with hundreds of holes and many components, it's not really realistic to expect a data-driven model to train on the full model at once. And it's, at least from our experiment, it seems to work better when we can work on local views of the object. And every time you work on local views of the object, like what you're seeing here, there are all these questions of how do you train on this subset? And then after you have your prediction on these subsets, how do you stitch everything together so that you can get a global prediction of the entire model? And in this specific work, what we also figured out is that it's a good idea to try to always use the right representation for the problem. And for the case of features, we found that representing the feature as implicit line on a scalar field defined on a surface is actually favorable compared to try to classify the sharp features directly, just because it's very unlikely that the sampling of your point cloud will have samples that land exactly on the sharp features. One thing in general that happens whenever you try to work with 3D geometry is that you have this major problem of picking what is the representation that you want to use. And the unfortunate answer here is that there is not a canonical way of representing 3D geometry. There are many ways of doing it, and depending which one you pick, you're going to have pros and cons. And what this means is that algorithm needs to pick one and then stick with it. And so there are many variations of algorithms that works on 3D geometry because they just work on different representations. And another thing that is very hard, and it's something that it's usually not really considered, and it's something that is very specific of working with 3D geometry, is that unfortunately most of the operations that we do are actually not possible to be computed exactly when you use floating point. Like a very simple example is just like if you're on a plane in 2D and you have two segments, like a typical operation is, let's find where the intersection lies. And this is just going to be a point, and you can compute it by simply solving a tiny linear system. Unfortunately, if you're using floating point, even this operation cannot really be done, in the sense that you're going to get a point in here. And now if you consider these two segments that you get here, you're going to discover that these two segments are actually not parallel, just because the intersection is not exactly where it's supposed to be, but there is a little bit of error introduced. And while this is something small, and you might think, well, why do I care? I can just ignore it. This is true, and this is actually what most people do. The issue with this is that whenever you are ignoring this problem and you are trying to run your algorithm on millions of inputs, at some point, this is going to fail. And if every piece of your processing pipeline has this like very low probability of failing, the more pieces you plug together, the more likely it is to fail. And at the end of the day, it's going to be impossible to use this to process large chunks of data. And at the other extreme is like you can try to handle all of these, but this usually means that you're going to have more complex algorithms or slower algorithms. And so there is really no free lunch here. You need to just pick whatever you like. And whatever, like, are you willing to tolerate failure or not? And the take in the work that we are doing is that we are not. And so we are trying to have algorithms, as you'll see later, that work reliably on large collection of data. And we are looking at them to have, on one hand, theoretical guarantees on the algorithm proof of correctness, but on the other hand, also practical evidence, statistically relevant evidence that the algorithm works and doesn't fail, even accounting for floating point rounding or other implementation issues. An example of why this is relevant is that one of the first steps before you do anything with geometry is usually to convert it into a different format or change the resolution. And this is what is usually called mesh generation. And in this example here, we took a data set. This is the Fingerton case. This slide is from a few years ago. And it's made of 10,000 models. And these are triangle meshes. And we try to convert it into a volumetric mesh so that it can be used in a simulation pipeline. And the sort of surprise here is that if you try them on this arbitrary collection of data, they're going to fail most of the time. And this is something that it's not really tolerable if you're trying to automate. And I would like to point out that in here, having a number that is like 99.9%, it will probably still not be enough. Let's say that you're trying to use all of these to process a data set like ShapeNet so that you can do, I don't know, you can try to learn policies for a robot to grab an object. Even if you take only 0.1% of ShapeNet, that's going to be way too many models to try to clean by hand to just make them mesh. So we really want to get to a point where things work all the time. And this is the overall goal that you're going to see appear many times during this talk. So the reason why this specific problem is hard is because whenever we look at geometry, we look at it and we think, okay, well, this looks reasonable. This is like the side of a watch. But when you look closely, you're going to see that there are issues. And these issues are hard to see, but very annoying. And in particular, let's look at on the back of these, they can be like really, really horrible. And the question is, if you have this, what do you want to do? And my take on this is that what you want to do is to just get rid of all of this. Like, who cares about all these small details? We just want to clean it up. The problem is that deciding what to keep and what to not keep is not easy. And if you want to do it in an automatic way, you need to have an algorithm that even if it's given this horror, is going to be able to make it to the end and then figure out what to clean up. So this is something that we work on for a long time. We started in 2018, and then we had like one SIGGRAPH paper per year, improving over this technique. And now we are to a point where I'm reasonably satisfied with the quality that we have. There is still quite some work to do in terms of speed. But we are to a point where we can take these large collections of models and we can convert them reliably to any auto representation that we are interested in. and especially like prepare them for simulation or for conversion to other formats. And the sort of key idea here that makes all of this work is the use of what we call an envelope. So whenever we load a geometry in whatever format it's given, we don't assume that the input is perfect. We just assume that the input has problems. And then we allow our algorithm to do tiny, minor variation of what's happening close to the input geometry to eventually fix it. And this is what we call an envelope. And this concept is quite powerful and allow us to do, to get like 100% success over this data set, and also larger one that we tested later on. And it allows you to do things like what I'm going to show in the next slide, where you start from some geometry that is partially broken, it might have low quality, and you just pass it through this black box, and what you get out is a clean mesh, and where you can configure what is the resolution and what is the output format that you might want. And the algorithm is going to hallucinate certain things. For example, there is a hole in the bottom, and the algorithm is just going to decide to close it. So it's going to make arbitrary decision if a geometry is not clean, but it's going to give you the expected answer when the geometry is clean. So the idea is going to be that if you provide something reasonable, you're going to get a reasonable output. If you provide something unreasonable, we're going to do our best to clean it up, and we cannot really guarantee what you're going to get in the end. But we're going to still guarantee that you're going to get a clean mesh that is going to be manifolds without intersections, and something that you can still use in existing processing pipelines. This is an example of a model that I showed before that is cleaned up by this. You can have like collection of very thin features. The algorithm does not really care about this. You can use this as a way to clean up models. You can have models with self-intersections or weird patterns, and this method is going to clean it up and give you back a mesh at the resolution that you desire. And you can even use it for doing more complex operations like Booleans between objects directly in this representation, and you can even mix and match different representation for the different pieces that you plug together. So this was a very quick summary on our effort on data generation. So I strongly believe that while it's hard to collect 3D data, this is a really important part if we want to make progress, both on the geometry processing to design algorithms that are robust, and on the data-driven side, because it only makes sense to, like we saw that for images and other kind of data, usually data-driven algorithm works well when there is a large data set available, and it's likely that the same thing will happen for 3D geometry, with a major difference that collecting 3D data is way, way harder and more expensive than for images. Another issue that is specific for 3D data is that conversion between different formats is very hard, and it's useful, I believe, to have tools that allow you to go at least to one canonical format that for what we are doing is a triangle mesh. So we can take different format, clean them up until we get a triangle mesh, and then have additional procedure that convert it back to whatever other format you want. But I think like focusing on a specific one will allow us to have something that is more reliable and more robust and still sufficiently flexible to support a variety of applications. One surprise is that we spent a couple of years trying to add semantic informations to ABC, where we had many mechanical engineering students classify models for us. And then after 2 years of work, we actually had to give up on this effort because we realized that at this scale, when you have so many models, even human annotators are unable to do a good job. Like what we saw is that we were not getting consistent labels from the human's annotator to a point where it was unreasonable to even try to use this data to train an algorithm. And again, we didn't use like random people on the Mechanical Turk. We actually had a group of master students specialized in mechanical engineering to do this job, and even them, they were not able to do this in a reliable way. So what we are converting this whole effort is to go for a unsupervised clustering approach, and this is something that I'm hoping to be able to share soon. I hope in the summer we're going to have some preliminary version of this deep clustering data set built on top of ABC. Another effort, which is something that we are doing in collaboration with both Autodesk and Adobe, is to try to get to a point where specifically for computer-aided design models, we have a canonical format and a canonical open source geometric kernel that is able to take this geometry and convert it into the typical representation that are used for deep learning. And this is a pretty major effort, and my hope is that we're going to have it out before the end of 2021. And we are hoping that this is going to become a sort of standard for generating data sets for 3D deep learning. And we are hoping in the long run to also have this integrated into the Autodesk tool so that it's something that is going to be also easy for people to directly use and help us out in this effort. If you're interested in any of these or anything about this talk, of course, just feel free to ask questions. I am monitoring the chat, or if you just want to send me an email after the talk or in the discussion after the talk. Okay, so this was the first part of the talk on gathering data. Now, something more of what you can do with this data. And one of the things that I work on for a while, and I think it's an important topic, is on using all this data to streamline and help people acquire additional data. And in particular, if you use before a 3D scanner, I'm not really referring to scanning 3D object by taking pictures. I am more talking about like being willing to invest arbitrary money in having an expensive scanner and expensive hardware dedicated for scanning. But even there, if you want to scan arbitrary objects, well, there are efforts for specific feature, for example, for scanning faces that are completely automated. But when you want to scan arbitrary objects, the procedure is still slow and quite inefficient. It usually requires to like rotate the object around to get it into multiple view. This can be automated to a certain extent. There is usually some manual labor to figure out what is noise, what is not, how to register the different scans, how to fill gaps that you might not have seen from certain views. And this whole procedure is still, despite like the huge interest in these, both in academy and industry, and the practical relevance of this, is still a procedure that is quite hard to fully automate. I mean, you can go most of the way there, but at the end of the day, you're going to probably have someone go manually and clean up things in every scan. And I think like this is a perfect place where trying to use data-driven methods could help, but at the same time is extremely expensive to acquire data, but we can use for training data-driven methods to solve this task. And a common approach that has been used before is to try to simulate. So what you could say is you have a certain scanner, and now you try to calibrate it as well as you can, and then you try to use the virtual simulator to generate data that you can use for training, and then apply these also to real images. And going in this direction, what we try to do is to figure out if we can actually push this idea to the limit where what you get out of a simulator is so close to reality that you actually cannot distinguish it from the pictures that you get out of a simulator. And to our surprise, there are almost no papers or works that try to do this. Not that to a point where like there are works that are trying to do it, but there is nothing that is really trying to use as the metric for success. I have two images and I just subtract them pixel-wise and I cannot tell what is the difference. And so we work on this for a couple of years, and I'm going to share some preliminary results that we have. So here, like one of these images is the actual picture coming from the camera, and one of them is the simulated image coming from our simulator. And to make your life easier, especially considering that Zoom might be compressing it a little bit, this is the just pixel-wise difference between them. And it's probably not easy to tell here which one it is. The answer is that this one is the actual picture, and this one is the simulated one. And the difference can even be, so this is what we did only after our preliminary calibration, like this is only hardware calibration. And then we can actually get them to be really identical. These are the new differences after the update by doing a little bit of further tuning of the parameters of a simulator later using a differentiable rendering approach. So the final answer here is that we can get to a point where we have a simulator of a scanner that is essentially indistinguishable from reality. And this also means that if you now train on data generated from the scanner, this data will very likely generalize to real data just because there is no difference between the two. Of course, this is not something that you can do for a completely arbitrary scene. We had to make assumptions on what can be done here. But I think this is an important step in the sense that this will allow you to have a baseline of on any data-driven technique that is going to help reconstruction methods, that is going to say, like, what is the best that you can hope to achieve? Like, it's going to be very hard to get something that is better than working on perfect data and on data that you can generate freely as much as you want. And so, like, after there is this baseline, I think it's interesting to say, okay, but what if I don't want to invest all this money in my scanner? What can I do with a cheaper one? And of course, it's going to be worse, but at least you have an idea of what is the best that you can do. And I think this is an idea, this idea of like being willing to get perfect data and see how far you can go. It's something that is not typically done in the computer vision community, but it's something that I personally really, really like because it allows me to focus on one specific problem at a time and to have like very clear baseline of what can be achieved and how much can I push it. So how did we did this? So the ingredients here to make this scanner and simulator work is that we calibrated it using components that were CNC milled from aluminum with a tolerance of very extremely strict tolerance, so that we know already what is the shape of the object at a resolution with errors that are way below 1 pixel of our camera, so that we can trust the geometry that we get from here. One of the major challenges in this project was to actually paint this object. It's surprisingly difficult to paint an object without changing its geometry and to get a uniform painting. And so this is something that costed us like immense amount of time to do it right. After you have the geometry, we built a hardware scanner built mostly from out-of-the-shelf components, but everything was built in such a way that the calibration procedure does not take 10 seconds as in most commercial scanner, but in our case, it takes around an hour of actually like acquiring images and processing. So with this expensive calibration, we can get it to a point where we don't calibrate only the most obvious parameters like extrinsic and intrinsic parameters of a camera and projector, but we also account for the focusing, special configuration, or the distortion introduced by the lenses, imperfections in many of the different components, both on projector and lens and camera, and so on. So by doing all of this, we can push it to a point where the differences are below a pixel. And then the final thing is that we are working in a controlled environment where we can control both the lights and the materials that we are working on. The cool thing is that after you calibrate the system in this way, you can also use it on more complex material, on color material, on specular one, and so on. But at least for the calibration, these are the ingredients that are needed. And one of the things that we are doing now is to prepare the release of all of these that we hope to do in the summer, where we're going to release the entire hardware blueprint and the entire software for doing calibration and simulation. But also we are going to provide a large collection of objects that have been already pre-scanned and everything that is coming from our calibrated hardware. So we hope that it's going to be possible to use this data set and this simulator directly, and people can do experiments on data-driven method for reconstruction without actually having to reproduce the entire hardware from scratch and just using the data that we provide. Our hope is to keep the hardware setup at NYU for a long time and to also help people that need to scan specific object by scanning it for them, but we'll see how far this can go. But we're definitely going to release the entire specification so that other people can also reproduce the setup. So now that we have this, what can we do with it? And I'm going to show like a few applications. This is all still quite preliminary, but I am excited about this direction because it allows us to do quantitative evaluation of algorithms. For example, here we are looking at reference geometry. This is the CAD model of our pawn, and then we are scanning it virtually with different settings. And now the question is, if I want to reconstruct these point clouds that I'm getting, and I want to use Poisson reconstruction to reconstruct them, what are the parameters that I should use for Poisson reconstruction to get the smallest error? And this is something that you usually don't do. Usually you just play with these parameters until you get something that looks right. But what you can do now, and I'm excited about this, is that you can say, well, since I know what is my ground truth, I can actually run Poisson with different parameters and check which one results in the smallest error, so that from now on, I know what are the right parameters that I need to use for Poisson for my specific setup to get the best accuracy. And now all of this can be done in a quantitative way and in an automated way, because it doesn't matter how many parameters you have, you can always do like grid sweeps and until you find what is the best setup. In a similar spirit, one thing that is difficult to do is to filter noise, because in many papers that are working with noise, you usually assume some model of noise, some synthetic model of noise, and you try to get rid of it. But what you can do now, since we can simulate the scanner at this level of faithfulness, is that we can actually learn how to denoise the specific noise introduced by our scanner. And this involves like going from like problems on the lenses to the sensor to the geometry and so on. So it's a more realistic setting, and it's a setting where it's possible to show that data-driven filter have obviously an advantage against the one that don't have data, because they have access to a lot of extra information that is very difficult to quantify in any like direct analytical way. Other thing that we are working with is that we can try to use this to do depth completion, to complete part of the models that you never saw. And also here, you can use the entire ABC collection, for example, to scan, to generate virtual scan of mechanical component, and then use this data to complete a scan. And since everything is done in this way, where you can simulate it, but it's actually matching reality, you are working in this like ideal setting where you can generate as much annotated data as you want, as long as you're willing to have a HPC cluster with enough machines to run all this computation that is needed to generate all this data. All of this is path traced, so like rendering all these images require quite some computation. Okay, so this is a summary of this project. It's something that I cannot share yet. We are still wrapping up the hardware description, the software package, and the data set, but I'm hopeful that we're going to be able to have all of these out in the summer. And in case you're interested in using this before, do send me an email. I'm going to be happy to share something preliminary already before, if as soon as it's in a state where we can release it and make it run on other machines. Let's see. Yeah, so in general, like the idea here is to have ideal framework where you can train your model on synthetic data, know that it will generalize on real images because they are sufficiently close, and have this like idealized setup where you can measure how good a certain argument that you are developing is in a quantitative way and in a simple way. Then, I mean, in the future, we plan to extend to additional material, more additional lighting setups. But I think this was the first step, and it was a first step that took us quite a long time of engineering to get to a point where we can get this pixel-wise matching. Okay, so this concludes this second part of the talk on using this large data set for some data-driven task that in this case involves acquisition, and this was done by simulating light. And now I would like to move to the last part of the talk, which is about simulating deformations. And in particular, all of these will be tailored, as you'll see later, for generation of data for supporting reinforcement learning for robotics applications. And just a few words on physical simulation, right? It's something that has been going on for a long time. This Antikythera mechanism was an analog computer that was developed by the ancient Greek, and it has been used for doing long-term prediction of astronomical position and eclipses. And from there, we of course made huge progress, right? To the point where we can now do complex simulations on our laptops or even our phones. And these are just a few examples of things that are typically done now. You can test how mechanical components behave under a certain load and how the stress distributes, so that you can figure out how and when it will break. This is used for aerodynamic simulations to figure out what is the flow of air around airplanes or other devices. It's possible to use this to simulate car crashes, for example, to decide how to optimize the components to minimize the impact of the people that are inside a car. So there is a lot of wonderful things that you can do if you can simulate deformations. And unfortunately, like while it's possible to do all of these, doing this sort of simulation has a massive human cost. And I would like to give you here an example of what I mean. Human cost in the sense of like hours of expert people that needs to work with software to get to a point where they can simulate. So here is a first example. So we have 2 boxes on the sides and 2 boxes in the middle. Think of these as like just boxes of some material, let's say rubber. And I want to do something pretty simple. I want to say one box is glued to the table, so it cannot move. And the other box, on the other hand, I'm holding it with my hand and I can move it around. And now I want to just take this one on the right and move it on the left and see what happens to the one in the middle. Okay, so this is a very, very simple situation. And this is an example of a commercial software, and we subscribe to their software support, and we tried to run the simulation, and it didn't work at the first try. And what you're going to see now are every bubble is an exchange with the support where we try to understand what is going wrong, and we learn that like, well, but the contact formulation only works for stationary problems. You should use a small amount of compression. Why don't you throw out this checkbox about augmented Lagrangian? Oh, but this is symmetric. You should have made it symmetric. Oh, wait, don't do nonlinear, use linear strains. Maybe you should do an auxiliary sweep. And it just went on and on. Like every one of these was interaction with them, with a team of support that is specialized in helping people get the simulation out of these. And after a while, this converged to the following, which is, but you're using a triangular mesh. There is a value that causes problems. It's unclear why this is happening. But if you use a parametric step size of that specific number, you will find the expected solution. If you use another one, it might not work. And so the problem I have with all of these is that on one hand is extremely inefficient. If for one simulation that is even simple, you need to go through all of these. As things get more complex, it's going to get just worse. And but this is something that you can think of like, I can solve it by just throwing money at the problem. If I have enough people, I can do this. I still think it's unrealistic to expect that, for example, for reinforcement learning, you might be willing to go through all of these for every one of a million scenarios that you might want to simulate. But let's say that we have unlimited money and we can do this. I will still be not happy with it. And the reason I'm not happy with it is because what we're trying to do, let's say for reinforcement learning, we're trying to learn a policy for controlling how an object is being grabbed. I am using a simulation to avoid to have to do this experiment in reality because it's expensive. And I want to do this simulation because I want to know what it would happen if I have this set of initial boundary conditions. But now, if I need to tune a gazillion parameters and the result clearly depends on all these parameters, and then I need to look at the result and decide if it's good or not, if I need to tune it more or less, this is not something that I can use to predict anything. Or at least like, it's kind of strange that I have a bunch of knobs to tune, and depending on what I pick is going to give me a result or not. How do I know if I can even trust what I got there? And also like, why do I need to tune all these numbers? What I want is just move my box and know how it behaves. And so similarly to what I discussed in the beginning for dataset processing, also here, our goal is to essentially get rid of all the parameters, get to a point where the user is going to specify what they want and everything else is hidden. It's just hidden behind a black box algorithm that is going to do whatever it has to do. And in the end, it's going to tell us, okay, your box is deformed in this way. And not as existing methods do, that are going to give you something like this. And then you can probably figure out that if it's a physical simulation, you cannot have blocks that are overlapping. So you know that something went wrong. So how can we get to this point? So first of all, like, what are we really trying to do? What we're really trying to do is to have the user specify some geometry and then specify some boundary condition. For example, for this example of a chair, the weight of a person that is going to sit on the chair. And then we just want to press a button, wait for a while, and get back the answer, which is the chair going to break or not? In this case, it will. And then if you know that it's going to break, you can go back, maybe fix your model, add some reinforcement, run the simulation again, and see that it doesn't break anymore. And if you can make this thing fully automatic with no user interaction at all, then you can even imagine that there is not going to be the need of a user deciding to add this reinforcement, but you can have algorithms that are going to figure out automatically what needs to be added to achieve a certain goal. And we would like to have all of these not only work on this small, simple chair, but on real complex objects like these ones that are here. These models are courtesy of Anthropology. And where the example on the left, we are optimizing this geometry to remove volume while still keeping it structurally sound. And on the right, we are optimizing the geometry, this geroid geometry, to increase heat flux. This is a device, it's a dissipator where you can like use this to transfer heat from air to a liquid. And so there are many cases where automated simulation is useful. One is, for example, robotic manipulation, where you want to learn how to get a certain piece and you want to train it on a large collection of hundreds or thousands of variation of a geometry. And you simply need to be able to do this automatically. You cannot expect some human to spend hours on every model just to make sure that it goes through. Other things that are interesting is like optimizing geometry so that it deforms in specific ways, so that you can have mechanisms that are built in the material instead of having them done explicitly. It's starting to become more and more common to have prosthesis design in a customized way for a certain patient. So you want to go from medical images to geometry, and you want to simulate what the prosthesis will do when it's embedded in the specific body of a patient. And for robotics, maybe you have only one single geometry, but you need to run a lot of simulation, like what OpenAI did for this Rubik cube solver, to account for all the possible configurations that allow these robotic hands to behave and solve a Rubik's cube similar to how humans can do it. And like the major challenge here is not really in simulating the elastic deformation by itself. For this, we have very good models, but is figuring out how to handle contacts. And this is something that we first explored for a year and a half, and we found that none of the existing contact formulations were actually suitable for this treatment. Many of the existing methods, both in graphic, in scientific computing, in mechanical engineering, are designed to be fast and efficient for a given scene, but assume that there is going to be a human tuning parameters. And what we want here is something different. We want something where there are no parameters to tune, apart from like the material parameters. Of course, you want to specify these. But then like we don't really care about cost as long as it's going to make it to the end reliably. And we can trust the result that is going to be faithful to what happens in reality. And one of the major improvements that we did in this series of work, this is a collaboration between NYU, Adobe, and UPenn. We have multiple papers in this direction. The original one was published last year, and this is IPC. Then this year at SIGGRAPH, we are presenting an extension of IPC for rigid bodies. And another work that was important is this one here that actually allow us to have hard guarantees on the correctness of the algorithm. And what we do here is essentially, instead of using the traditional approach to contact handling, which is wait until some contact happen and then activate some forces to prevent it, but being okay with small interpenetration as long as are small and we can somehow fix them. Here we take a very different approach where we reformulate the entire problem as an unconstrained optimization, where we have a line search that explicitly prevents intersection from ever appearing. The method is more expensive than existing simulator, but it can reliably handle very complex cases like the one that you see here on the right. So there are quite a lot of differences with traditional simulator, from how the contacts are modeled. Like the model does not assume that the forces are only added when the model exactly touch. The model is going to add them forcing the object to be slightly separated, which is actually what happens in reality. If you have two objects that are touching, they're actually going to be bound together. Like it's not possible for this to physically happen. They're always going to stay at a certain distance. But I don't have time today to go into all the details of this, and I just refer you to the papers to know more. But I just wanted to show you some of the things that you can do with such a framework. like the key difference here, for every law you see different scenes, and for every column here you see different approaches, different methods for solving these that are published in the literature. And green means that it succeeded for the specific selection of parameters. The other color means that it failed for different reasons, like they took forever or crashed or the physics blow up. And what you see is that for most of the scene there is green, meaning that for all these methods you can find parameters that work. But the fact is, if you're trying to do a sweep on some parameters like the density of a cube or the size of a cube, you don't want to have to tune the parameters for every case. And this is what IPC fixes, because now in our case with IPC, you might get like more computational expenses depending on the scene, but you're always going to get a valid result, which is what we were targeting here. And so you can do pretty crazy stuff. Like this is this example of like really trying to break it. I mean, you probably never want to simulate something like this, but we can. And this shows that even in crazy examples, you can still get something reasonable. You can more easily match reality. This is a golf ball made of foam, which is shot at high speed to a wall. And what you can see here is that at the top, it's our simulation. On the right, it's recorded footage. And you see that they are remarkably close. And you can even see in the bottom how the shockwave propagates after the object hits the wall and bounces back. And so it's exciting that you can now use these to simulate. And in this case here, we used IPC, run it with, instead of doing a proper material calibration first, what we did here is run IPC with a lot of different variants of possible material properties until we find one that is actually matching with our foam ball. And all of this is only possible because now running a simulation, it's easy. You only need to specify your boundary conditions and you're going to get an output back that you can then, in this example here, try to match to the result of physical footage. The formulation naturally supports codimensional objects, which is something that sometimes it's useful to save time. This means that you just have, like, in this case, like individual triangles that are acting as collision objects. It has correct handling of friction. In this case, this arc is staying together thanks to friction and gravity. And more recently, we extended this to work in the setting of rigid body dynamics, where every object can only be transformed by a rigid transformation. This is an example of a model that we downloaded from the web and just directly simulated in our setting. This is an example of a pretty challenging case of having this bolt fall into a screw. Having correct modeling of friction means that we can trust it when we try to use these, for example, in a robotic simulation. And we can do more changes, like have massive differences in mass of the object here and still get a result that is physically plausible. And we can go for more complex scene, like this chain that is being rolled up with a very heavy anchor in the bottom. It's still something that we can directly simulate. Of course, like as the complexity of a scene increases, the computational cost of simulating this increases too. This approach is far from being real time. We can simulate complex mechanisms, and overall, like the motivation for doing this is something that any bikers in the audience here will appreciate, that we can simulate a bike chain. And here we are simulating literally every piece and every component separately, and then like the simulator takes care of how the physics will look like. Here is another example that looks similar to many other simulations that you might have seen before in computer graphics, but with a big difference that in here, every frame is guaranteed to be free of self-intersections. Here is just an example of what happens for different friction parameters. This is an example of a collection of cards, and then we drop some objects onto them. This is an example of the codimensional simulation. And here is a very difficult example where you have a codimensional chains, and then we drop a heavy ball on it, and still we get a result that is physically plausible and no links breaks or start to fly around. In the same spirit, like with a similar formulation of this idea of starting from a valid state and always keeping it valid and having this idea of recasting everything as unconstrained optimization, we used a similar approach for optimization of drone trajectories. So this is a paper that is going to be presented at ICRA. where we use a similar idea to optimize drone trajectories in indoor environment, and where we have strong guarantees on staying in the same homotopy class and guaranteeing to always have a valid path. And here is just an example of how this will look like in a more complex scene. And yeah, I don't have much more time to comment on this, but I encourage you to take a look at the paper in the top left if you're interested. Okay, so to conclude, like I find very important, especially for everything data-driven, but in general for every research that is done in computer science, to try to make the research that we do reproducible. And in the specific case of what we are doing in the lab, since what we are doing is trying to develop tools that are useful for other researchers, we strive to make all of these not only available on our website, but also easy to use. And we strive to maintain it. In particular, I just wanted to spend a few minutes just going over some of the packages that might be of interest to everyone that listened to this talk. We are now exposing everything that you need for many of the things that you saw in the talk in Python. And this is all the code that you need to do the simulation of the chair that we saw in a few slides ago. So the packages that are useful are, this is what you see here is the actual code that you need to simulate that chair. There is a first piece, which is the wild meshing part, which is the part on generation of meshes, both 2D and 3D. It's all available on Conda, and it's all free to use, even for commercial purposes. There is another piece, which is how do you transfer boundary conditions from your input to the simulation mesh? And this is something that Zongxi has been working on for a while. And if you're interested in this, I refer you to these two papers that are showing methods that allow you to do remeshing, and at the same time, keep this correspondence between the input geometry and the simulation mesh and going back and forth. Then for the actual simulation, we developed a software that implements a finite element method that is called Polyfem. And this is also free. It's on Conda, can be used freely also for commercial purposes. And it supports many of the common physics. It has fluids, elasticity, heat diffusion, and it's something that has been designed to be used on an HPC cluster. So you don't need licenses, you don't have dependencies, and you can very easily use this to script it and use it, for example, for data generation in a machine learning pipeline, where you need to simulate physics. And it's already there, but we're going to make it official with a tutorial and everything in a few weeks. Everything that I showed about contact resolution, it's also going to be integrated in Polyfem together with all the code that is needed for doing the elastic simulation that you saw before. And then finally, there is a lot of generic geometry processing, loading models, saving them, smoothing them, visualizing them, and so on. And this is something that it's a long time that Alec and I have been trying to maintain and push forward libigl. And right, like the library continues to proceed. If you're interested in helping us out and in contribute, you're very welcome to. And right now, we recently released a Python version of this. It's also available on Conda, and it's directly usable. And most of the library is already exposed, even if you're not yet at 100%. So to put all of this together, if you are interested in how to use the code, we have at this URL tutorial that is pretty long. It's all on YouTube of videos that are showing how to use all these different components and how to use them to solve a certain set of problems similar to the one that I discussed in this talk. But the focus is not on the theory part or the research part, but it's more on like the low-level details of how do you run it, and everything is done with like live tutorial in front of Jupyter notebooks. So one more thing is that all these libraries are using NumPy and SciPy as the way to exchange data, so they're very easy to be integrated with standard machine learning pipeline like as TensorFlow or PyTorch. Okay, so just a few words to conclude of what is my vision for the next few years is to go from a point where working with 3D data, right now it's a task that requires expertise, a lot of hours, knowing how to use tools that are pretty advanced, especially on the simulation side, and some of them are also very expensive. But at the end of the day, all of this will require a lot of manual interaction. And so the goal is to go from this situation where you need to be an expert to be able to work with 3D data to a new position where it's easy and it's free in the sense of like, you don't need to pay licenses for it, and it's easy to deploy on clusters so that you can use it at large scale. And I think like going toward this goal is important. Like I believe that one of the reasons why machine learning has exploded in the last few years, I mean, in addition to being useful to solve a lot of practical problems, is because there were companies that invested in excellent tools that are taking care of most of the low-level problems. How do I get something to run fast on a GPU? And how do I deal with all the compatibility problems with a GPU? And the fact that there is this software that allows you to focus on what matters and takes care of all the boring things, it's, I think, an important motivation, an important reason why all of this happens so quickly and why so many people are able to do research in this area. And I think this is something that we didn't do right in our community of processing 3D geometry, where it's very difficult to find code that works reliably, and it's very hard to get it to work for a specific problem. So my hope is that it's going to be possible to proceed in this direction with libraries that are getting closer and closer to these, to TensorFlow and PyTorch, even if for now, unfortunately, we don't have the backing of large international companies. But my hope is that at some point, this will happen when these tools will become more and more important for pipelines that are processing 3D data. So this concludes my talk. I would like to use this occasion to do some shameless advertisement of postdoctoral positions in our group. So if anyone is interested, please send me an email. And I would like also to thank the NSF, Adobe, Autodesk, AMD, and Entopology for funding this research and making it possible. And I'll be very happy to answer any question that you might have.
Okay. Thanks, Daniele, and for the wonderful talk. So we will have about a 30 minutes panel discussion where Holly and Vova will chime in. Okay, so before doing that, so there's one question from YouTube. So I'm just curious about all the forward simulation shape. Is the shape optimization, or right, it's really about the simulation part, right? Or these forward problems or inverse problems to control the parameters, and what is the role of machine learning in those?
Mm-hmm. So the question is like how does simulation fits in like data-driven and machine learning?
Yeah.
So there are like, I mean, I see like multiple scenarios where this is useful. And this corresponds to like large branches of research in machine learning. So one of them is in scientific computing, where there are some physical phenomena where it's just not known what is a good physical model for them. And in that case, machine learning is useful because it can be used for like complementing existing simulators for some parts of it where they just don't know how to simulate it. Another one, which is very popular in the machine learning community, and I think at least right now, the results are not to a point where they can be used yet, but they are promising, is where you can use machine learning to replace expensive simulations. For example, like some of the simulation that I show in this video, some of the fluid simulation, they could easily take like hours per frame to run. And if you need to repeat like the same simulation over and over again, and you could like approximate all of these with data-driven model, this in theory would have potential huge benefits, right? Because you could get it, first of all, you could get it faster to evaluate, better map into the hardware. And at the same time, if you manage to approximate it with deep network, the deep network is by construction differentiable. So this is something that is very useful for doing inverse design. Up to this point, there are not many clear cases where the networks can actually beat traditional methods for a given accuracy. But it's a direction that many people are looking at, and there are starting to be some promising results in this direction. Another thing, another direction that is the one that I was most focusing on for this talk is that there are cases where you would like to train on real data. For example, for robotics, let's say that you're trying to train a robot for walking. And one way to go is definitely to just constantly run your robot, and every time it falls, figuring out that was not the right thing to do. But this is extremely expensive because you need to run the actual robot for millions and millions of times to get the data that you need to train your control model. This is something that I think some companies try to do, at least for robotics arm. And my understanding is that it's so expensive that it's not really viable. And I'm not aware of any direct result at large scale that has been done in this way. So one typical thing that one tries to do is to avoid this crazy expense and use simulation as a surrogate for getting enough data to at least initially train the model. Maybe you're going to fine tune it using real data, but at least in the beginning, you're using a simulation. And in this setting, the properties that I think are important for the simulator are, first of all, that is faithful to what happens in reality, because otherwise the model is not meaningful. But then the second property that I think is important is that you're going to use the simulator by taking a scene, and then you're going to have something happening, meaning the boundary conditions are going to change. And then you want to know how will the scene look like after half a second for a new set of boundary conditions. And you will need to do this millions of times for different set of boundary conditions, depending on how the training goes. And what is important here is that the simulator is going to reliably give you back something that makes sense, because otherwise you're going to learn noise. And that's something that there are a few videos online that you can find where, for example, control methods learn that if you are very smart and you for certain physical simulators, you can actually generate energy. So you can actually find sequences in the simulator that tricks it to actually generate energy, so that you can, for example, have a robot that instead of walking, it can fly. And of course, this is completely unrealistic, but the reinforcement learning algorithm can figure out these problems in the simulator and take advantage of them. And so on the other hand, if you have a simulator that is faithful to reality, it will not be able to do this and actually learn how to walk instead of how to fly, which would be nice to have, but unlikely to happen with a biped robot. Okay, thanks.
Okay, so maybe next is that we go one round of questions from the panelists, and then all of us will have some discussions about the broader impact of this. Okay, so maybe we start with Hao.
So Daniele, it was a super impressive talk. I really like the work you're doing. I think it's really, really useful. And maybe before I ask my question, I think just to add to the previous question, I think it's really, really, I mean, this is basically what computer graphics, the whole field of computer graphics or geometry processing does, which is trying to simulate how the real world looks like and works. And the huge advantage is that it goes way beyond VFX or video games. It's really about how do how can you make something appear as real as possible? And people are doing the same thing for rendering, for instance. For example, people are training how cities look like so that they can teach self-driving cars to navigate around real-world cities instead of taking only real-world video footages. So I think what Daniele does is really important, because it's, it's sort of taking the simulation approach in addition to that, which tackles exactly the problem of how can you just collect so much data without actually doing it? And that's, I think, really the power of what computer graphics really does. So actually going to exactly that point, which is you have this, I think it's a really interesting work on how do you simulate a scanner. It's a great idea. I have actually two questions on that. So first of all, I think you didn't mention too much how exactly you're trying to simulate. And also, is it very specific to a type of scanner? Is it only structured light scanner, or does it work for any kind of? Because I think what would be really, because the problem is, I think there are many different kinds of scanners. There the ones that you mentioned with multi-view, the passive one, the active ones, the LiDAR ones. Right. Is there a way to generalize that to many of them, or?
Yes. So what this work. Thank you for the question. So like what we tried to do here was to see, like, pick the setup that will allow us to be more in control, right? Just to like see like how far you can go first. But what we discovered is that at the end of the day, like the important components are applicable to any kind of scanner. And like the important ingredients here is getting extremely good calibration objects. And this is something that surprisingly you cannot even buy, which is something that is puzzling to me, but it's not something that is commercially available, because like calibrating with checkerboard is one thing, but calibrating with an object that is actually 3D, it gives you like a lot more flexibility in what you can do, and it allows you to check if things are really correct or not. The other thing is that the actual procedure that you use to calibrate, it's important. And usually like relying on just a few images of a checkerboard is not enough. So what we ended up doing here is to have a robotic stage that actually allow us to get hundreds or thousands of images and then average it all. And this like gives like huge advantages in the accuracy that you can get if you're willing to invest more time to calibrate.
I don't know if you remember, like back in the days, like maybe 10 years ago, when we used to publish papers, you know, people always ask, oh, do you have ground truth examples? And then to get ground truth, you basically take a synthetic model or something that was someone generated, and then you just project it to get like the the partial scans that are kind of simulated. So I think that's like a super cheap version of what you're doing right now.
Yeah, it's like, but so what we are doing here is it's like there is a lot of technical effort in making it work, right? But at the end of the day, like the surprise is that like the main difference here is that we are not comparing qualitatively. Like the whole goal here is to get to a point where the comparison that we do is just like pixel by pixel. And then as soon as you have these, because you now have this like measure that it's objective, then I think like everything becomes easier, because then now you can trust it and you can build upon it and whatever you're trying to do with it. And at the end of the day, like getting to a point where you can do it requires to be very careful with the hardware and how you calibrate. But at the end of the day, it's a more complex pipeline for doing calibration, but it's relying on all the techniques for computer vision, for calibrated scanner and projector that have been introduced over the years.
Right.
And I think it would be exciting to try it on other scanners. Things that we want to do is, for example, try it on an iPhone scanner. And all of this is possible, but I feel like it was like the important step was to just make it to a point where we are sure that we can, because now from now on, like we know what is the maximum that we can achieve, and we know that everything that any extra error that is added on top of this, it must be due to using like more economical hardware or whatever other conditions we cannot control.
So let's take the iPhone example. Which challenges would you see? How can do you think it will out of the box have pixel accurate simulation, or do you think there's some things you need to do?
My biggest worry of trying to work on an iPhone is what kind of processing is done on the raw data that we are not gonna see. And I have no idea how this is gonna be. So what we did here is like we use a commercial camera where we can have like raw readings from the CCD. And we discovered that this is super important because, for example, like many cameras have like corrections for broken pixel, or they do like crazy averaging when there is like a pixel that doesn't have the right like binning. And so like all of these, it's easy to deal with if you have control over it. But if you have all these like automatic ways of fixing the image that you get, it's going to be harder and harder to control. But we didn't try yet, so I don't know. Like this is like my biggest fear is this one.
After this talk, they'll know how to denoise it.
Yeah.
Okay, for the interest of time, let's move the question to Wola, who is at Adobe.
Yeah. Thanks, Peter, for organizing. This is a great venue. I'm really enjoying the talks, and thanks, Daniele. I really appreciate all the effort you make in making your code available and usable. It's always like for any intern that we have, libigl is one of the tools that we direct them to, and it was great. I actually learned today about all the other kind of Python compatible software you have, so that's very good to know. So I think you mentioned a few very good motivations for doing robust physics and robust kind of geometry processing for data generation. And there is one more that I have for all this workflows, and I wonder what's your take on this, is that there are very often in this machine learning pipelines, right? We want to encode some kind of learnable component that says, okay, there is ambiguity in terms of semantics, there is ambiguity in terms of what maybe physics would do, there is ambiguity in what the world is like, and then you have to make some inferences, you have to make some approximations, and that's where you want to use kind of raw neural networks that just like take data and try to approximate it. But at the same time, there are often cases where you don't have ambiguities, right? Like we know often how to have mechanics, right? Like we know certain laws of physics that always work. In surface reconstruction, we often know that you want to reconstruct a manifold at the end. You want to reconstruct a closed surface, for instance, or like genus of the surface and things like that. And what we often find useful is that sometimes you can think of simpler techniques that would be actually differentiable layers of the network that would take some input that's ambiguous and project it to something that's robust and guaranteed to give you a feasible output, right? And in the context of physics, right, it would be awesome if I could take this IPC, right, and have it as a layer in my neural network, where my neural network makes some predictions, let's say, about the parameters and initial conditions, and so on and so forth. But the output is always going to be a plausible physical simulation, just because my layers that are going to produce the output are forced to be something that's guaranteed to be correct. And I understand in this particular case, we are not quite there just because of all the computational expense and so on and so forth. But I would love to hear your vision of like, do you see simpler methods appearing that are robust and become integrated in these neural pipelines?
Yeah, I think this is a very, very good question. Instead of just using let's say black box, like data-driven model, like if you could built in some knowledge of a system that you're trying to simulate. And there are many, especially in the scientific ML literature, there are quite some papers that are going in this direction. And what they show is that it makes a huge difference if you have some of these invariants either directly in the architecture or maybe you keep them in the loss. But one of the things that unfortunately, it's happening, at least for trying to use networks to help or approximate physical simulation, is that usually papers don't compare with traditional approaches. So while there is a major gap in terms of so the way I see it is that if you're doing physical simulation, what you're trying to do is to spend. So you have a certain accuracy that you want to reach. And now the question is, how much time do I need, computational time do I need to reach this accuracy, right? Or if you want to flip it, you can say, I have 10 seconds, how much accuracy do I get in 10 seconds? And while it's true that adding this extra structure in these methods dramatically helps improving their accuracy, as soon as you actually compare them against simple integrator, like Euler integration, it's very hard to get any benefit from using the data-driven method for that setting. And so at least I'm not directly aware of papers that can directly use these extra invariants, at least for physics simulation, in a way that it clearly gives you, I don't know, a factor of 10 or 100 performance boost compared to traditional methods. Methods are getting better and better, so I think it's a very exciting direction to look at. But I think one of the important things whenever physics is trying to be integrated with a data-driven method, I think it's also very important to always compare against methods that are not data-driven, just to have an idea of how far we are from what people have been already using for the last 30 years.
But there could be applications and use cases that are maybe not in the setting where you just want to reproduce the simulation. So I have hard time coming up with this for physics example. But for instance, in the shape reconstruction, right? Like maybe I want to have a TET mesh as an output, but my neural representation just by default spits out a point cloud, right? Or some kind of surface model. And so instead of trying to use this TET meshing as a post process, I would like to be a layer in my neural network that spits out the point cloud and then gets projected into the volumetric representation. And the rationale for not using it as post-process is that neural network would somehow learn what kind of surfaces it would generate so that it's easier for the TET meshing algorithm to output a volume.
Yes, in that case, you'll probably want to be able to differentiate through these blocks, which like at least for the tetrahedral meshing method that I showed, it's something that cannot be done right now. But one of the cool features, I actually didn't mention it yet. It's something that like we briefly discussed in the paper, but we didn't use it for anything yet, is that the formulation of IPC, like the one that you're seeing here in this video, the entire formulation, both the deformation part and the contact response and the time integration, it's all differentiable. It's not formally, but for practical purposes, this is differentiable. So like this whole formulation could be used to do like, to integrate it in a network, and you should be able to differentiate through these layers. At least for now, these were required to define the differences, that it's very expensive, but it's probably possible to also like extend this construction to have a more efficient evaluation of derivatives. Which will like probably for many robotics applications that involve rigid bodies will not be so relevant, just because you are working with so few parameters that it doesn't matter. But definitely if you want to work with like deformable objects, then something more efficient needs to happen to be able to differentiate through.
Okay. Thanks, Vova. Thanks, Daniele and Hao for this round of questions. So I prepared one question, very general question, really about, I think, about how to feed with them the geometry processing in this AI era, right? So I think all of us started in geometry processing. We are still in geometry processing, there was a conference called Symposium Geometry Processing. All of us have published in that venue, and also segwell. But the interesting is that all of us also moved to publish at CVPR, right? So and this is general AI conferences. Of course, we still publish segwell. So I want to get a sense of, for example, what would be, for example, the bidirectional synergies. So what is really the impact of this kind of this deep learning in geometry processing? And on the other hand, what would be the impact of geometry processing, in particular, like representations of three-dimensional geometry, right? So that is critical for machine learning. So what would be the impact of geometry processing in this AI at large, right? So I would like to hear opinion from Hao first.
I think it's a really good question. And I've actually put some thoughts around that. And I actually wondered myself why I'm publishing more in vision these days. But I think it's not about whether I like one field or more than the other, or I think one field is more important than the other. I think it's in the nature of it, because if you start with, I mean, I've been always working on things about 3D reconstruction or digitizing things, or scanning things. Now, when you think about this problem, it's an inverse problem. The inverse problem, and it's, Daniele also presented some of that, which is you start basically with the image and you try to reconstruct the scene in 3D. Now, what's interesting is when you think about from a deep learning /AI standpoint, most of there's a huge amount of applications that are published in vision conferences, and the initial ones are, and I think it's normal that they are all vision based, means that we have all these explosions of things like nerves and all these visual representation, trying to bypass the need for even geometry, right? So if you look at a lot, there's a trend where people are trying to, you started to have all these object recognition kind of papers, and then it's all images. Then you have all these neural rendering things, synthesis, GAN synthesis, it's all images. Even though we started to do some hybrids with, these are very graphics oriented papers, but for most vision things, they try to do things as implicitly as possible. But it does. I think that the next stage actually will come back into 3D, because in the end we still live in a 3D world. It's not just light fields. So to get an understanding of like how spatial things work, I think this is so. I think it's just a time thing. Like it starts off with like where everyone just works on anything that has an implicit representation of things, and then the next stage, I think people will come back, and I think Daniele is kind of like really ahead. He's already thinking about like simulation, right? So I think all these, I mean, it's basically like the inverse pipeline where you, instead of going from modeling to rendering, you have like rendering and then the animation, and then, you know, you basically have the other way around. So and maybe I'm completely wrong, but this is kind of how I see the trend, at least from my standpoint. And for our purposes, for instance, you know, we care about realistic digital humans. We care about these things. It's natural that we will focus first on the rendering part, which is, well, let's do it in a neural way. Well, let's use neural rendering, or let's use GANs to generate very realistic things, because that's the shortest, that's the lowest hanging fruit. But then afterwards, once you need to have control over it, once you need to animate it, then you care about, well, what about behavior, right? Okay, let's process videos. Well, you know, right now I really need to have the person interact with things. So I think in this sense, I think the geometry comes back again. So I think that in a, not even like extremely long term, but probably the next stage, the geometry will become really important. And I think we can see like, you know, all this stuff that Daniele was doing, Boba was doing. You know, we also started looking into things like differentiable rendering, right? So how do you connect the 3D and the 2D? And there's many people working on differentiable rendering. So I think those pieces will start off slower. And there's another reason. I think it's not just because it's not only application driven. I think the other thing is just simply because 3D is more heavy than 2D. So I think the challenge in 3D is like, how do you handle the memory, right? And how do you, I mean, it's just, I mean, this additional dimension basically gives you just so much more in terms of memory requirements, which I think is another reason why, you know, it's harder to collect data. It's harder to do this. So there are many reasons for that.
Yeah, just to add to this, I think what Hao kind of highlighted correctly is that, you know, representation is really a big fundamental problem in computer vision too, right? And we worked a lot on representations that work for like graphics problems, for rendering pipelines, but we don't really know yet what are the good representation for vision. And I think CVPR and this kind of vision venues now exploring this a lot, where there is like very limited boundary, little boundary between graphics and vision and geometry processing, and people are really experimenting and trying to figure out how to represent natural phenomena, because at the end, there is something out there in the world. You're capturing it with cameras, you're capturing it with scanners, and so on and so forth. But then you just want to build a representation that sometimes is a mixture of things that we know is true from physics, or we know works from graphics, and this new representation that we are just learning to figure out how to use is this like neural networks with the massive amount of data they can store and optimize for.
Yeah, okay, maybe we Daniele need to bump up. What
sure.
Yes, I have like, what are your insights on this?
Yeah, I have an historical perspective, maybe like a bit far-fetched, but I do see a connection. Is that this problem of deciding which representation to use for geometry, it's also something that 30 years ago we went through in graphics, right? I mean, we started by trying to decide, like, we really would like to use triangles, but doing Booleans, it's very hard. So maybe we can use implicits. Then at some point, there was an entire branch with its own conferences on, let's not even use implicit, let's just use points. We can use them for doing splatting. We can do a lot of geometry processing directly on points. And I mean, and after like a long time, at the end of the day, we are using triangles for most of the things that we are doing. And the reason is that it's annoying and there are many problems with it, but you have this advantage of being able to be adaptive, which is something that allows you to scale to very complex models. And And like for like most like entertainment application, we're using triangles, maybe on top with subdivision surfaces. For CAD application, in some sense, we are using curved meshes, right? It's still a mesh. It's not made of triangles. It's made of quads for mostly historical reasons. And there are splines built on top of them because it allows you to have like less degrees of freedom so that you can actually edit them more easily by hand. And that's where most of the things are, right? The only like exception to this is in additive manufacturing, companies like Entopology are now exploring again the use of implicits. But at the end of the day, if you want to simulate something or render something, it's very likely that you're going to convert it to a mesh. And so like I wonder, like this is starting to look quite similar to what's happening in machine learning for 3D geometry, where like people started to try to use just octrees for volumetric representation. Then at some point we had points. Now we are moving to implicits. And my guess is that at some point, probably we are going to move back to meshes because for the same reason that graphics stayed there and ended up converging there.
Yeah, I think this is great, all great insight, right? So I think representation, finding suitable representation is a critical problem for machine learning in 3D geometry, right? I think what Hao mentioned, right? So like different application simulations, inverse problems, those are highly tightly connected with this. Okay. Really thanks Hao and Voa for the panel discussion, and again thanks to Daniele for the wonderful talk and sharing, and also for sharing the insights. Okay, so this concludes this seminar series, and we'll have a break next week for the NIP submission, right? The deadline. Okay, thanks everyone.
Thank you.
Thank you.